We've all felt it, right? That little shock, that surprising spark. But can we actually explain it? Well, today, we are pulling back the curtain on a phenomenon that's both super familiar and way more powerful than you might think: static electricity. Let's get into the science behind that invisible zap.
You know exactly what I'm talking about, don't you? That tiny, sudden spark that jumps from a doorknob to your finger, seemingly out of nowhere. What is actually going on in that split second?
All right, so picture this. You're just walking across a room, shuffling your feet on the carpet, maybe in your socks, not thinking about a thing.
Then you go to open a door. Your hand gets closer and closer to that metal handle. Everything seems totally normal, right?
And bam, there it is. That sharp little spark jumps from the doorknob to your finger. It's an experience pretty much everyone has had, but you know what? It's not magic. It's pure physics.
To really understand that zap, we have to zoom in. I mean, way in. We need to peek into the invisible world of atoms, because that's where this whole story really gets started. So when you boil it all down, static electricity is just what it sounds like: an imbalance of electric charges on something. The static part just means those charges are hanging out, building up, and basically just waiting for a chance to go somewhere.
And what are these charges exactly? Well, the main characters in our little drama are these incredibly tiny particles called electrons. They're kind of restless, and they're the ones causing all the commotion. So how does that imbalance of electrons even happen in the first place? Well, it all comes down to a little move we can call the electron swap.
It's like a simple three-step dance. First, you've got contact. Think your socks rubbing on the carpet. Second, you get a transfer. Some of those jumpy little electrons literally leap from the carpet onto your socks. And third, separation. As you walk away, you take those extra electrons with you, leaving the carpet with a positive charge. And just like that, you've created an imbalance.
Now, the materials involved here are super important. Things like that carpet or your wool socks are insulators. They're great at grabbing and holding on to those extra electrons. But you, your body, and that metal doorknob, we're conductors. We let electrons move around freely. So you've basically turned yourself into a walking, talking, charged-up battery, just looking for a place to discharge.
But you've probably noticed this, right? It seems to happen way more often in the winter. What is up with that?
Is it just a coincidence? Nope, not at all.
The secret ingredient is humidity. In the summer, the air is full of water vapor, and water is a pretty decent conductor. It helps all those extra electrons on your body just kind of leak away harmlessly into the air. But dry winter air? It's an insulator, so that charge has nowhere to go. It just builds and builds and builds until you touch that poor, unsuspecting doorknob. Okay, so we get the tiny spark from a doorknob, but what's really wild is how this simple little principle can scale up from a minor household annoyance to one of the most powerful events in nature.
And once you know what you're looking for, you see it everywhere. You know when your clothes cling together in the dryer? That's just them swapping electrons as they tumble around. Rubbing a balloon on your hair to make it stick to a wall? That's a classic electron transfer. It's the exact same science behind all of these things.
But what happens if you take this same electron swap idea and you scale it up to the size of a massive storm cloud? Well, it turns out that this exact same principle is behind one of the most powerful and dramatic displays in the entire natural world.
Yeah, just look at that number. 300 million volts. That's what a typical lightning bolt can carry. And it's almost unbelievable, but it all starts with the very same idea that makes your socks stick to your sweater. You see, inside a big storm cloud, ice crystals and water droplets are rubbing against each other constantly, creating a massive charge imbalance. So lightning, it's really just nature's way of balancing the books. It's a giant zap between the cloud and the ground. So this force isn't just about random shocks or terrifying storms. We've actually gotten incredibly clever about controlling and using static electricity. But as you can imagine, it also comes with some pretty big risks. On the good side, we harness this for amazing things. Photocopiers use static cling to get toner to stick perfectly to the paper. But there's a flip side. A tiny static discharge, one you might not even feel, can completely fry sensitive electronics. And around flammable stuff, it can be a serious fire hazard. So when you really think about it, from the way paint gets that perfect coat on a car to the way lightning forms in the sky, this invisible force is constantly at work all around us. It's a fundamental part of our world that we've had to learn to both use and respect. And that kind of leaves us with a fascinating thought, doesn't it?
That simple zap from a doorknob proves a fundamental truth, that tiny, invisible interactions can scale up to create massive, world-changing effects. It really makes you wonder, what other unseen forces are quietly shaping our world right now?